Welcome back to the second part of this lecture 8. So, as you have seen, we have been discussing about the tensile testing and the various strength and ductility parameters. We talked about strength, yield strength, UTS, fracture stress, and then in ductility we talk about percentage elongations and percentage reduction in the area. So, let us now see actual values of the stress and strain. Typical mechanical properties are measured at room temperature. It can be measured at high temperature, low temperature also, but typically we measure at room temperature, and these are the values it shows. So, let us take aluminum. Aluminum alloys has very low strength, something like yield strength is 35 to 55, and UTS is something around say 900. So, that means that is aluminum and an aluminum alloys, right, that is why it is shown like that. Then your elongation can be something like 45 to 50. And some zeros have got deleted because of the size of the table. And I did not talk about Poisson ratio, that is also important parameter. Poisson ratio is talk about the ratio of radial versus axial deformation. If you deform any material in tensile strength, what will happen? There will be two kind of strain. One is the increase of length, other is the reduction of the area, right. And it is not always true that both the things will be same. So, depending on the type of materials, there will be variations. So, Poisson ratio for metals and almost close to 1/3 or that is 0.3 to 0.34. Copper alloys are much stronger, and as you can clearly see that the strength of copper alloys are much higher. It can go up to 1100 MPa yield strength, UTS even much higher. Then there are many steels are more important, you should use these values. And tungsten and alloys is 0 elongation, but very high strength, you can clearly see. Then I had given you some properties of other non-metallic material like diamonds, even rubber, thermoplastic, thermostats. You look at it at your own space. I do not want to spend a lot of time on this table. Look at your own space, because you should know these values, some idea of the values, because you are going to design materials, discover new materials. So, you should have fair amount of idea of these values. I am not saying that you should remember, mug up, no, but get an idea of what the range is in which the values of strength, ductility can vary for each set of materials. Well, we talked about mostly parameters, so tensile stress parameters related to the original area and original length, right. But as you know, that is not the case always, because as you are deforming the material, the area also changing as well as the length. Only thing which is remaining constant is the volume of the material, right. As we already talked about it, that A0 L0 is equal to A into L, right. Original area, original length equal to length, area and length at any time during deformation. So, that means what? The stress and strain which you are measuring using the original area, original length will not be correct when the material is getting deformed. So, what you do? You take care of that part using the actual or instantaneous area or instantaneous length. So, two new parameters comes into picture, true stress and true strain. True stress is what? This is equal to force divided by the instantaneous area or actual area at any point of the during the testing. True strain is basically nothing but change in length divided by the actual length or instantaneous length, dl by L. Remember the engineering strain was change in length divided by the original length. Here we are changing the definition. What is that changing? We are changing is basically delta L by L. So, total strain is nothing but integration L0 to L dl by L, that is equal to log of L by L0. Am I clear? So, this is the difference between true stress and true strain vis-a-vis engineering stress and engineering strain. Please keep in mind these definitions are very important, because true stress, true strain can be used when you process materials using deformation processing. Engineering stress, engineering strain are used for design of any component. If you want to use any material in actual application, what kind of parameters you will be using yield stress, that is why your UTS there you are going to use or original length and original area. One can actually convert, or one can get relationship very easily from true stress to engineering stress and true strain to engineering strain. They are in the book of George G. Dieter, you can easily find out. More accurate measurement should be what? This way, like force versus intensity area, or here you can see even if you can consider diameter also. So, what you see is this 2 strain is equal to 2 log of d0 by d, or d0 is the original diameter and d is the instantaneous diameter. Well, I have given you the relationships, you can clearly see here for this 2 stress and 2 strain with 2 stress the engineering strain, and therefore 2 stress is equal to engineering stress plus into multiplied by 1 plus engineering strain, and 2 strain is nothing but log of 1 plus engineering strain. This is very easy, you can also do that, so no problem. So, how does this 2 stress 2 strain curve will look like? Well, 2 stress 2 strain curve will never go down as the engineering stress strain curve does. You can see engineering stress strain curve is behaving like this, but 2 stress 2 strain curve is going up and up. That is because you have taken care of the change of area or the length, that is why. Otherwise, this should have been behaving same way. This gives you much better perspectives in terms of how the material is behaving. So, there is nothing like a going down like a engineering stress strain curve. Please remember these aspects. Well, this is in a nutshell showing you everything. 2 stress 2 strain versus engineering stress strain curve, and at this 2 strain at the UTS or the peak of this engineering stress strain curve, your strain is equal to the strain hardening coefficient. We will talk about a little bit later. So, you know this portion of the curve, engineering stress strain curve, the linear nonlinear portion of the curve can be fitted with a equation, and that equation is basically this, which is known as a flow curve, which is nothing but sigma t is equal to k multiplied by epsilon to the power n, where k is a strength coefficient and n is the strain hardening exponent, because it is in the power, that is why it is called exponent. So, this curve is defined by this equation. This equation is very fundamental, because it talks about 2 important material parameters, one the strength coefficient k, other one is the n or strain hardening coefficient. Why it is called strain hardening coefficient? Very easy to understand. As you clearly see, as the curve goes up, the slope of the curve is changing. Slope of the curve is actually gradually decreasing. That means what? Material is becoming harder and harder as you deform. As you deform, material becomes much harder. That is why if you take a piece of metal or steel, actually hammer it, after that if you measure its strength, it will be much stronger. By hammering, you are introducing a lot of defects, and these defects will increase the strength of the material. That is what is called as a strain hardening, and n determines that behavior. N tells you the strain hardening coefficient, how it is going to change as the material is deforming. So, these 2 parameters are fundamental, or other material properties. You should know it very carefully if you want to design new material. The constitutive equation is exactly like this, sigma is equal to k epsilon to the power n. You can put t also, does not matter, but that is a 2 stress actually, by the way. This is 2 stress, that is why it is called sigma t, better to put sigma t, otherwise you will not forget, and epsilon is 2 strain. And you know, if I take log on the both side, what do you get? You get this curve. So, if I plot log of, let us say if I plot log of what? Log of epsilon, so log of sigma t versus log of epsilon, what do you get? You get a straight line. Very easily you get a straight line, right? The straight line is what? Straight line is this equation, and this straight line, slope of the straight line will give you the value of n. Slope of the straight line will give you the value of n, and this intercept will give you value of k. This is evident from this equation itself. So, one can measure these 2 parameters from this, and I am giving a list where the values of both k and n are given. N is always less than 1. You can see here in this chart, maximum value of n is 0.49, that is for the brass, 70-30 brass, copper zinc alloy. Most of the cases values are even close to 0.1, less than 0.1, and k can vary depending on the type of material. So, that is what is to be also taken to be consideration when you want to design materials k and n values. Well, there are different types of flow behaviors for a material. Like if a material is ideally plastic, they will start deforming at from the 0 stress, or as you not 0 stress, as you increase the stress from 0. It is ideally elastic plastic, then initially it will deform elastically, then it will become plastic. And third one is called piecewise linear, where this part is linear and this part is non-linear, but one can actually make that as a piecewise or piecewise linear, but that is an approximation. Mathematically that is a curve. Well, there are many other parameters which you also need to consider. Energy absorbing by a material is during deformation is very important, because that is what tells you how much energy it can absorb before it fractures. So, there are two parameters for that. One is called resilience, that is the ability of material to absorb energy when deformed elastically, and it will return back or return to its original shape and size when you unload. That is called modulus of resilience. This is what is used in the golf bat. The material which is used to make golf bat must have very high resilience, because it is going to impart the energy from the bat to the ball, but material will never deform plastically. So, therefore, during hitting of the bat to the ball, when the bat hits the ball, a lot of energy is absorbed by the material. It must have the ability to absorb the energy, otherwise it will break. That is why resilience is very important when you want to design a new material for the golf bat. Okay, there are many other instruments which will require high resilience. I am just giving you only one example. You can see how the golf bats are used by the different players in the TV or in the internet, and you can understand how important is this. The sports goods are very generic ones, which requires design of new materials. So, how do you measure the resilience? It is measured by the modulus of resilience, that is the strain energy absorbed per unit volume, and this is nothing but area under the curve. So, you could have seen that if I draw the stress strain curve, it looks like this. Yes, see, the curve looks like this. So, this part of the curve is your elastic portion, right. So, area under this curve is what is known as the resilience, and that is nothing but half into yield stress, this is the yield stress, this is the height of that triangle, into strain, that is what it is. And you can convert this using Hooke's law. So, this will become yield stress square by 2 into elastic modulus y, because E 0 is equal to sigma y divided by E, that is why. So, hence this is what is called modulus of resilience, very important parameter if you want to design new material. So, for golf bat you would like to increase yield strength, decrease E, right. As you decrease E, you will increase, as you increase yield strength, you also will increase, and effect is more subtle or more pronounced when you use high value of yield stress, very subtle, because it is a square term. And therefore, the design, or when you discover new materials, you need to discover one which has very high yield stress. That is, to be specific, metallic glass is used in the golf bat, because metallic glass has a very high yield strength. It can be having yield strength of 3 to 4 GPa. You probably may not have heard it, very high yield strength is possible in those materials, okay, but it has very low ductility. It does not matter, because here material is not going to deform plastically for the golf bat. Another important parameter is called toughness, the ability of a material to absorb energy in the plastic range. Remember this curve which I talked about it, this curve, this is the plastic range, right. This particular portion of the curve, the right side, that is called the plastic range, this one, this is the plastic range, and area under this curve is what is known as this toughness, because that is the area, this area indicates amount of energy absorbed by the material when plastically deformed, and this is very important. Why? Because real applications, many of the materials plastically gets deformed, and when they plastically get deformed, they have to withstand this occasional stresses of the yield stress without any fracture, and this is desirable in many components. You can think of cycle pedals, you apply a lot of force, but it never breaks, because it has a huge toughness. So, toughness is very fundamental parameter, and I am showing you the how two different categories of steels, high carbon spring steels, which is used in the trains as well as in the cars to absorb the vibrations or absorb the impact loading. High carbon spring steel has much higher resilience compared to the structural steels. You can see the area under the curve, right, very easily. So, that is why almost all the springs are made of high carbon steels, which contains a lot of silicon. So, whether it is in trains or in the cars or in the trucks, this is what is used as a important material to design this kind of, or use this to make this kind of components. Well, some of the values of these provided here, modulus of resilience. You can see the high carbon spring steel has a very high resilience, almost 10 times higher than the medium carbon stainless steel. Similarly, rubber has also very high resilience, you can see 2140, but metallic glass has a surprisingly order of magnitude higher resilience, 30,000 kPa. That is why for the golf bats metallic glass is used. Even all these projectors, you see electronic projectors, right. In the projector there are many mirrors are there, which is used to project in the using computers, right. So, there these glasses are used for making these mirrors, because they also have very high resilience. Well, that is for the resilience. Now, what happens in fracture? So, fractures can be two types, brittle and ductile. Ductile fractures have necking, and this kind of things happen. You see there is a neck and then followed by pores or bubbles, and then this bubbles basically, these are basically small pores, they join and they form a crack, and then it breaks down. You looking at the crack surface, you can clearly see whether it is a ductile fracture or a brittle fracture. Brittle fracture will have flat surfaces, ductile fractures will have a cup cone type of surfaces. You can see this is a cup, this is a cone, right. So, that is by looking at that you can determine that. This indicates the behavior of material. Remember, fracture will be able to change depending on the temperature. Some material may be ductile at room temperature, but brittle at low temperature, liquid nitrogen temperatures. Many applications requires you to discover materials which will be used at low temperatures, like cryogenic engines for the space applications. Well, so how does it happen? For the ductile fractures, as I told you, the necking happens in the materials, and then there is a small pores forms. These pores then join and form a crack, and these cracks actually then separate these two pieces. On the other hand, for the brittle fractures, you will not have much significant plastic deformation. That is why they look like a flat, and in many cases you can have also shear bands, but 45-degree angle with respect to the loading axis or this axis. That is very common in case of fracture. So, this strength of material or ductility of material depends on temperature also. I already talked about it, temperature has a strong effect on that. So, as you see, if we increase temperature, both yield strength and ductility, yield strength and tensile strength decreases. This is very important if you want to use some material at high temperature, like in case of turbine engines, we have talked about it. On the other hand, ductility will increase as a function of temperature. As you increase temperature, ductility is sum to increase. There are exceptions of that also, but in general this is what is this trend is followed. So, strength and ductility behave in the opposite way as a function of temperature. This is the real experimental curves, steels actually, mild steel at 400 degree room temperature and minus 196 degree temperature, that is at liquid nitrogen temperature. So, as you what you see at 400 degree is very ductile, but strength is low compared to at room temperature as well as low temperature. At low temperature strength is very high, but ductility is poor. So, therefore, you have balance of strength and ductility as a function of temperature, that you must remember when you want to design material for application at different temperatures. This is also shown here, different kinds of metals like nickel, iron, moly, tungsten, tantalum. Remember, nickel is FCC, whether tungsten, tantalum, moly and iron as BCC. So, that is why for nickel you do not see much change of yield strength, little change as function of temperature, but for iron, tungsten, moly, tantalum, there is a massive change of yield strength, very massive change. You can see yield strength drops as you increase temperatures to 600, 500 degrees Celsius temperature, that is very evident. Well, what happened to ductility? As you clearly see, nickel ductility does not change much, it remains 80 to 100% as you increase temperature, but for iron, moly, tungsten, tantalum, all of them ductility goes down to 0 at low temperatures. These are actually body center cubic structure metals, nickel is per center cubic. So, it is very clear structure determines the property. So, for the per center cubic metals there will be no brittleness at low temperatures. For the BCC structures material will become brittle. That is why we define a ductile to brittle transition in case of body center cubic or hexagonal closed pack structure materials, but for the per center cubic structure there is no such thing possible. So, I think stop here because we have been discussed a lot of things in the last about 50 minutes or so. So, please keep in mind that these are very vital things to understand when you want to design something new, because if you want to design using machine learning you will be using a lot of features or a lot of parameters, and these features will be these aspects like resilience, ductility, strength, UTS, fracture. These will be all used as a feature or parameters, but now without knowing these aspects you cannot design a new material, right. That is what you should have a fair idea what these parameters are, how they are measured, and what is their behavior in terms of different materials as a function of different temperatures as well as a function of different stress, a different type of loading and strain rate. Some of this we will discuss in the next lecture also, but this fundamental knowledge is very vital for you to take forward. Otherwise, you will be using all these parameters for design of any new materials using machine learning without knowing them, and that will give you wrong results, or rather that will give you non-interpretable results which you yourself will not be able to interpret it, and that is basically useless. If you want to produce something which is not interpretable, that is not useful to mankind, and that is why fundamental understanding of these kind of parameters are very important, and that is the reason I am spending so many lectures on the structure property correlations in this part of this course before I take off different machine learning algorithms and give you different kinds of examples. So, I request you to go through these slides and lecture as well as this book if possible in a detailed manner, so that things are very clearly understood to you. So, let us stop here. Thank you. We will see you in the next lecture.